Everybody, welcome back. This is Chapter 9 continued, and this time we're going to be talking about the Bohr model of the atom with orbits. So our goals in this section are to define an energy level in terms of the Bohr model, and then to discuss how the Bohr model can be used to explain atomic spectra. So to start out with, elements have unique light emissions. What this means is that the light frequencies emitted by atoms are mixed together so that we see a blended color. So if we think of a prism, remember from before, prisms can take mixes of colors and separate them out into individual bands. Well, if we have a mix of color from an atom or element, what was done is in the late 1800s by Ångström and Balmer, they took individual elements and they basically energized them and got them to put out some light. And then they put that light through a prism, and what they saw is that different elements emitted different bands of light. So the first element might emit, some blue and some red. And then they tested a different element, and the other element put out a different blend of light. Maybe it had some green and some light blue, and some yellow. So the different elements have their own unique blends of light. And if you send that blend of light through a prism, you can separate it into individual bands called a spectra. So this light that was spread out so they could see these individual wavelengths, and we know that we can correlate wavelengths to frequencies, so they could see the individual frequencies and wavelengths. This is what's called an emission spectra. They got elements to emit light by energizing them. They added energy to the system by hooking them up to some electricity. The elements then emitted light. They basically started to glow. And they took that light that was being emitted, they put it through a prism, and they noticed that individual elements have these unique bands of light that they're emitting. So this is what we call an emission or atomic spectrum. It's the unique pattern of light obtained when an element is subjected to some heat or electricity. So this diagram kind of shows what happens, right? You have a gas tube that's filled with, say, whatever element you want to look at. In this case, it's filled with hydrogen. And then you energize it. So you add some electricity, usually heat or electricity. So you energize the element in this tube, and it will start to emit light. And we're going to talk about why as we continue to talk about the Bohr model, but it emits some light. And that's a mixture of all the colors together. There's going to be red, green, blue, whatever colors are being emitted. And then that's sent through a prism, and prisms separate light into bands of color. And so the mixture of light was separated into individual bands. And then we can use some cool electronics and detectors to take those bands of light and detect what wavelength they're at and what frequency they're at. So we can use a detector to figure out what colors of light are being emitted once we separate the mixture of light into individual bands. And then we turn that into what's called an emission spectra. It basically separates out the colors of light and tells us the wavelengths of each of the bands that's being emitted by this element. So this is an emission spectra for hydrogen, right? We were looking at hydrogen. So hydrogen has this spectra where it emits light that's red, blue-green, blue-violet, and violet at these specific wavelengths. And only hydrogen has this exact pattern of light emission. We put a different element here, got it to emit light, separated the bands, it would have a different pattern. So it's really cool because each element has its own pattern. We can use this to kind of identify different elements. And this is what NASA does with a lot of their space satellites. When they're figuring out what elements are on distant galaxies or distant planets, they're looking at the light emitted from those distant galaxies, like taking a galaxy light, essentially, and in a satellite, directing it through a prism, a detector, and then sending the data down to NASA. And they can be like, oh, cool. This has the emission spectra of hydrogen, helium, neon, and oh, carbon. Well, that's cool. There's carbon on that planet or in that galaxy. That means there might be life forms there, or there's hydrogen and oxygen. That means there might be water there. So this is used in a lot of different areas of science, this emission spectrum generating by energizing or collecting light from a sample, separating it with a prism into bands of light, and then turning that into an emission spectra with the individual wavelengths identified. So here's, and again, the emission spectrum for hydrogen. It has what we call 4 lines. These are the wavelengths. 4 lines, each at a unique wavelength. So the instrument that turns that signal, the bands of light energy, into a signal that gives us the wavelength and the frequency and like the intensity of the light, that type of instrument is called a spectrophotometer. It takes spectra and it measures them, spectrophotometer. So it can measure the wavelength of light for each of those bands. And then once we know the wavelength, we can use our equation C equals lambda nu to calculate the frequency if we know the wavelength. And we can further take this and calculate the energy of each of those bands of light using additional equations. So each element has its own unique spectra. So this is the emission spectra for iron. Iron is a much more complicated atom than hydrogen. If we compare these two, let's go back a slide. Right, this is hydrogen, it only has 4 lines. Hydrogen only has 1 electron, and these emission spectra are related to the electrons in the atom. So because hydrogen only has 1 electron, it has a really simple emission spectra. But we look at something like iron, right? If we check the periodic table, neutral iron has, 55 electrons? Of course, I don't have a periodic table out now. It has a lot more electrons, so there's a lot more lines possible in the iron spectra. So again, scientists, we use like space probes and satellites equipped with spectrophotometers to measure the light being emitted from distant sources, from galaxies and planets, to determine the elements present. So we can do this because of Bohr's model of electron orbits. In 1913, Niels Bohr proposed that electrons surrounding the nucleus are organized into what he called orbits. So before this, right, we had the Rutherford model of the atom, where we knew there was a nucleus that had the protons and the neutrons, and we knew the electrons were like around it, but we didn't really know how they were organized around it. Were they just like randomly spread out? Were they, like Bohr said, zipping around in these like circles, spheres around the atom? Like, how were they organized? And so Bohr proposed in the early 1900s that they're organized into orbits. And what he said was that these orbits are at discrete stepwise distances from the nucleus. So the orbits aren't like some gradual thing where an electron can be any distance from the nucleus. They have to be in these like defined regions, which he called orbits. Kind of like if you think of the solar system. We draw a little solar system here, right? We have our sun. My daughter would be so proud with my drawing, right? And then we have planets orbiting the sun. In fact, that's where he got the idea to call them orbits, right? We have our first planet, Mercury, Venus, Earth, etc. And the planets like stay in their place, right? They stay in their orbit. That's what Bohr is proposing for atoms, that there's the nucleus and then the electrons around the atoms are organized in these orbits, which are at specific distances from the nucleus. So these orbits are at these discrete, like specific stepwise distances from the nucleus. And what he said is that each orbit is called an electron energy level. So he connected that where the electrons are located is going to be related to how much energy they have. So he said that electrons that are located in orbits or energy levels closer to the nucleus have less energy. So this image is from your textbook, kind of illustrating the stepwise or quantized nature of Bohr's orbits, that the nucleus is like the ground. The first step would maybe be your first energy level, your lowest energy level. It's closest to the nucleus. And then if you wanted to go up a step, you can't go in between. There's no steps. You have to jump all the way to the next step. and that would be a little bit higher in energy. If you wanted to go up more, you'd have to jump, take a complete step to the next rung on the ladder, and that would be even higher in energy, all the way until you just kept going out and out and out. So highest energy. So he proposed that orbitals exist in these stepwise functions moving away from the nucleus, and that the farther the electrons are from the nucleus, the more energy they have. So the farther away they are, the more energy they have. So what this looks like in terms of the kind of new model of the atom is that we have a nucleus with protons and neutrons, and then at stepwise discrete intervals going out from the nucleus are these orbits. Bohr numbered them. So it starts at orbital number 1, n equals 1, and the next one is n equals 2, n equals 3, and they go up stepwise in increments of 1 in whole integer values going out from the nucleus. So in connecting this to our discussion about atomic emission spectra and why the Bohr model and atomic emission spectra go hand in hand is that, remember those atomic emission spectra that we could make atoms glow basically by energizing them? And then they like let off certain frequencies of light, certain wavelengths of light, and each atom, each element has its own unique pattern of wavelengths that it releases. Well, Bohr's model helps explain why that happens. So according to Bohr and his model, electrons can do what's called jump from a ground state, like a low energy state, to a higher energy state, higher numbered orbital, if energy is added to the atom. And this is like, it's like what happens with emission spectra. Engstrom and Balmer added energy to their samples. They heated them up or they added electricity. And then they saw the atoms start to emit these different colors of light that were specific to each element. So we can cause an electron to do what's called jump from a low energy state to a higher energy state by adding some energy into the atom. So we add some energy. We say that the atom is absorbing some energy. And due to the law of conservation of energy, that energy can't be created or destroyed. When the atom takes in this energy, it has to go somewhere. And so the energy that's, say, coming in from heat or electricity is transferred to the electrons in the atom. And they can do what's called jump. They're going to go from a low energy state, now that they gain some energy, to a higher energy state. And so let's say this electron jumped from the first orbital, n equals 1, up to an n equals 3. It had enough energy to jump 2 rungs of the ladder. We now say that this electron is in what's called the excited state. It's at a higher energy level than it normally would be at, because the atom had some energy added to it. That energy has to be transferred. It can't just disappear. And so it gets transferred to the electrons in the atom, and they can jump up to this higher energy state. What happens over time then is that the electron is going to do what's called relax. It can't stay in that excited state forever. You have to keep adding energy to keep them kind of up there. So if you add some energy, some electrons jump up to an excited state, then over time, sometimes very quickly, and sometimes it takes a while, the electron's going to relax back down. It can't stay up there forever, so it relaxes. It might go all the way back down. It might only go down like 1 or 2 rungs of the ladder. And so let's say now it relaxes from n equals 3, just down 1 rung to n equals 2. Well, if we put in enough energy to make it jump 2 rungs, but only relax back down 1, then there's still some unaccounted energy. Energy can't be created or destroyed. It's got to go somewhere. And so what happens is the extra energy, right? It absorbed enough energy to do 2 jumps, but it only relaxed down 1. That extra energy is emitted, and that's what we see as the light. And so that's what Engstrom and Balmer were observing when they energized atoms of different elements. They added heat or electricity. They were getting these electrons to jump to excited states. As the electrons relaxed back down, the atom let off some light. And because each element has a unique number of electrons, the ways in which these electrons were jumping up and then relaxing back down was unique for each type of element. So this explains kind of how they observe those light patterns with atomic emission spectra. It also supports Bohr's model of the atom, because when these electrons are jumping up and relaxing back down, they're emitting very specific, right, lines or bands of light. They're not emitting the whole spectra of light. It's not all blended together. They're emitting like very discrete wavelengths. And remember, wavelengths and frequencies relate to the energy of things. So they're really releasing very specific, quantized, like narrow range bits of energy when they do this. And so it supported Bohr's model of having these quantized or discrete steps separating the different energy levels of the electrons. That electrons weren't just like sliding, wherever in between here. They were going jump-wise between these different levels. And because they were going jump-wise, you got very tight lines or bands of light coming out of them. And so this also explains why some things, some atoms, will sometimes glow or emit fluorescence. If you can get an atom to keep electrons in their excited state a little bit longer, then it takes more time potentially for them to come back down. And we see that as like the atom continues to glow even after it's been excited, you get fluorescence. And then the last thing to note is that, again, the amount of energy that's emitted, it's going to be related to the amount of energy between these different orbital levels, right? It takes energy to jump from a low energy one to, 1 or 2 or 3 or however many higher energy ones. And so based on the amount of energy that's emitted, right, because energy can't be created or destroyed, the amount of energy of this relaxation must equal the amount of energy that's being let out. Energy can't be created or destroyed, so a whole bunch came in. It went to exciting the electron. The electron relaxed a little bit, and so the leftover was let out. And so we can figure out the difference between these two energy levels based on how much light was let out. And so this is the equation to do that. So the amount of light energy that's emitted when an electron relaxes can be determined by measuring the wavelength of the emitted light. And remember, we have detectors to do this, and we excite electrons by adding some energy to them. And they start emitting light. We can send that light through a prism, separate it into bands, measure the wavelength and the intensity. So we measure the wavelength of this emitted light, and then we can plug it into this equation here called Planck's equation to calculate the amount of energy that corresponds to. So for each of these steps, like an n of 1 to n of 2 jump, there's a certain amount of energy associated with that. For an n of 1 to n of 2 jump, right, if you're jumping 2 or 3 rings, there's a different amount of energy associated with that. So this is called, again, the Planck equation. And it's a little advanced. We don't go into it too much more than this in Chem 300, but I did want to show it to you. So when you get into Chem 400 and you start talking about this, you're like, oh yeah, I remember Dr. G, she mentioned something about the Planck equation and she was really excited about these electrons. Because yeah, just by measuring that wavelength, which we can easily do with our detectors and spectrophotometers, we can then calculate the energy that the electron, the energy change it underwent when it relaxed from a high energy state back down to a lower energy state. There's a new variable in here. We already know that c is the speed of light, lambda is the wavelength, and h is Planck's constant. And it's a constant value at 6.626 times 10 to the negative 34th joules times seconds. So again, the Bohr model of the atom and the emission spectra supported each other. Those lines observed in emission spectra represent the light energy, a photon, a packet of light energy we call a photon. So the lines observed in these emission spectra represent the light energy or photons emitted by an atom when the electrons in the atom move between these discrete energy levels, like those rungs of a ladder. And those energy levels are the orbits that Bohr had proposed. So if we wanted to calculate the energy for this emission line from hydrogen, where the wavelength emitted when the electron undergoes this relaxation is 486.1 nanometers, we can plug it into this equation down here as the wavelength, 486.1 times 10 to the negative 9th meters to convert nanometers to meters, use Planck's constant, the speed of light, and we get that the energy of that electron relaxation was 4.087 times 10 to the negative 19th joules. And every time you do hydrogen, its emission spectrum, you get these same 4 discrete energy jumps or bands of light. So Bohr's model was a huge breakthrough, right? That thinking that electrons were organized into these orbits and being able to connect his theory to what we were seeing in the real world with emission spectra. But it only worked really, really well for atoms that were simple, that had like one electron, like hydrogen. When you started trying to use the same model and approach of like an electron jumping from one to the other in like a 1-by-1 fashion, it didn't work well for atoms that had more than one electron. So for hydrogen, it works perfect. But you start to get atoms with more electrons, which is all the other elements except for hydrogen, his model started to fall apart. And so scientists weren't done with understanding the nature of electrons after Bohr's model. It was a huge step to think about electrons existing in these quantized energy levels, but it wasn't quite as simple as Bohr proposed. The levels weren't just these like orbits around the atom that electrons would just jump from one to the other, and that's all they did. And so it led to the development of the quantum mechanical model. This model proposes the use of orbitals instead of orbits to build upon the Bohr model. So it allows for a more complex organization of electrons into regions that are now called orbitals. So before, Bohr's model just thought hydrogen looked like this, right? It was like a nucleus with some rings around it, and that was it. But with quantum mechanics, we know electron orbitals now can have all these different shapes. And these different shapes can be at different distances from the nucleus. And so the quantum mechanical model was able to supplement Bohr's model and fill it out in the areas where it didn't quite work. So that'll be the topic of our next lecture, the quantum mechanical model of the atom with orbitals. I'll see you then. Thanks.